Hi, everyone. So in this particular video, we're going to discuss what happens when you use a linear transformation in order to take an image of a basis of a vector space. What does it become? So we already know that if you take a basis for the vector space V and take the image of that basis under the linear transformation, you at least span the range. But we don't know, though, in the end, is that the entire space W, and we don't know if the resulting set is independent. So we have to fix those issues. And then finally, we'll have at the end a way for us to determine when a linear transformation has an inverse. Not how to find it, just how to go about determining if it has one. And we can get also to a really neat consequence that in the end of all the finite dimensional vector spaces, there's essentially really only one of any one given dimension. So let's suppose you have a linear transformation. Suppose B is just some linearly dependent set in V. We don't know how many vectors are in there. Then if you take the transformation to every single vector in B, we just normally call that T of B. That set actually has to be dependent also. Why is really easy, because if you have a bunch of vectors in B that are dependent, there's a linear combination of them that adds up to 0. But when you take the transformation of that equation on both sides, you get another linear combination, but those are vectors from T of B. And the scalars before one of the scalars is not 0, then one of the scalars later is also not 0 because they're the same scalars. So of course, T of B would also be linearly dependent if B is a linearly dependent set in B. But what we want is independence. So here's the exact same theorem, but I've changed only a little bit, and I highlighted it in blue so you can see it. Again, let T be a linear transformation that goes from V to W, but this time insist that's 1 to 1. Then if B is a linearly independent set, then when you take the transformation to every single vector in B, it will also be a linearly independent set, but that'll be in W. That's a pretty important result. We need to see why. So let's suppose that you have just a bunch of vectors in B that's in vector space V. So when you take a T and apply to each of these vectors and form a linear combination of those mappings, that you get the 0 vector. I'm going to prove to you that the scalars have to all be 0. Well, now, if that's true, you can use properties of linear transforms to get that has to be true also. Remember, the linear transformation of the 0 vector in V has to be the 0 vector in W. But then since T is 1 to 1, they have to be equal to each other. But the vectors V1 through Vn are all in B, and they are assumed to be linearly independent in the vector space V, which means that the scalars have to be all 0. If the scalars are all 0, then the vectors of T of V1 through T of Vn have to be linearly independent also. This shows you that if you take any finite subset of the vectors from T applied to B, that you have to get a linearly independent set. So the transformation applied to the basis, those corresponding vectors have to be linearly independent also. Now that we have that gives you a direct, easy consequence that if you have a linear transformation that is 1 to 1 and onto between two finite dimensional vector spaces, then T maps a basis of V to a basis of W. That they're finite dimensional actually does make a difference this time. It's really easy to see why. If you have a basis for V, then T of B is a basis for the range of T. We already know that because it has to be linearly independent and it has to span the space. But we know that since T is 1 to 1, then the range of T is W. So T of B spans W. But since T is 1 to 1, then T of B is linearly independent. So these T of B, the transformation applied to the basis of V, has to be linearly independent and span W. It's a basis for W. That's it. It's really easy. Also, we get another nice little consequence from that also. Remember, I've already shown you that if you have finite dimensional spaces and the dimensions are the same, if T is 1 to 1, you instantly have that T is onto. And if T is onto, you instantly have that T is 1 to 1. We also now can because of that last result, If T is 1-to-1 and T is onto, and you're between finite spaces, then the only thing left is that the dimensions have to be exactly the same. They have to be exactly the same for the result you just saw. So now that you have that, we can then discuss finally, what do we need for a transformation to say that the transformation has an inverse? So the theorem is that a linear transformation is invertible. It has an inverse if and only if that T is 1-to-1 and onto. Notice though that I'm not insisting that the spaces are finite dimensional. That doesn't have to be true. It does not have to be true. They could be infinite dimensional. It's actually fine. Now, this proof is really long. There's so many parts to it. I'm only going to do half of it because of that. I'll do the one that's interesting, which is that since it's 1-to-1 and it's onto, then it has an inverse. So let's just do that part. Suppose that T is 1-to-1 and onto. If it's onto and 1-to-1, then for every vector in W, there is exactly one vector in V, so that T of V is at W. Why? Well, because it's onto, there's at least one. That's the definition of what onto means. And since it's 1-to-1, there can't be two vectors in V that get mapped to W. So there's only one, at most, one vector. So there's one and only one. That means then that for every W, there's one V. That's a mapping. So I'll define it. So S will be a mapping that goes from W to V. So that S of W will be V if and only if T of V is W. It's obvious then that S of T of V is just V. It's literally just look at the symbols, you see it's true. That means then that S composed with T is actually just the identity element, the identity mapping on V. Similarly, you can see it also if you take T composed with T composed with S, you would get the identity mapping on W. So the only thing I have left to do then to prove that S actually is the inverse is, by definition, to be the inverse, it has to be a linear transformation. This is just a mapping. I haven't shown you it's linear yet. So let's do that. Let's just take two vectors in W and some scalar. Notice then T of S of U plus V has to be U plus V, because T composed with S is the identity mapping. So that's true. But U is T of S of U, and V is T of S of V. But T is linear, so then you can break that apart to get that. Notice the left-hand side is T of something, the right-hand side is T of something, but we know T is 1-to-1, so the somethings must be equal. So S of U plus V must be S of U plus S of V. That's one of the properties of bilinearity. I could, if you like, go through the whole process all over again, looking at the scalar in U to show the other property. I'm just going to skip that part, as I think you understood what I just did. This shows then that T composed with S in either order gives the identity mapping, and that S is linear. S is the inverse. So that shows you then that as long as T is 1-to-1 and onto, it has an inverse. I have not yet proved that if it has an inverse, then T must be 1-to-1 and onto. That proof, though, is very easy, and you can literally just read it in the book. Now, last thing then. For now on, if you have a 1-to-1 and onto transformation, linear transformation, we're going to call that an isomorphism. And the spaces are isomorphic. So why is that important? Well, it winds up being that if V and W are both finite dimensional, then they're isomorphic if and only if they have the same dimension. This is an incredibly important result. It means that if you look at all the spaces that are dimension 3, they're actually all isomorphic to each other. They are all essentially the same. All you're doing is renaming the vectors and renaming scalar multiplication and renaming the vector addition. It's essentially only one vector space. That's why we just spent, what, 12 weeks, 11 weeks studying Rn, because it's actually the only really finite dimensional space. The interesting spaces are the infinite dimensional ones. They're all different. Many of them are very different. So that's like a whole other course. That's not for us. So why this is true? It's obviously true in one direction, because if V is isomorphic to W, that means there's a 1-to-1 mapping and onto mapping between them. That automatically means that since they're finite dimensional, they have to be the same dimension. They have to have the same number. That's something we already proved. The other direction, though, if they're the same dimension, I have to show that there is a one-to-one and onto mapping between them. And it's really easier just to show you by example. So instead of doing the proof in general, let's just do it by example. The mapping is going to go like this. I'm going to say that S will be this span. So the mapping T will go from P2 into S by, I'm just going to map a basis of P2 to be the basis for S by just doing this. T of X would then be E to the X, and T of X squared would then be E to 2X, and T must be linear. This will then definitely create a one-to-one and onto mapping. The reason why is very easy, because we already can see that the dimension of P2 is equal to the dimension of S, and that is 3. So all we have to do is to prove that this mapping is one-to-one or that is onto. Either one will work just fine. But notice that if you take any single vector you want, take any single vector in S, any vector in S can be written as C1 times 1 plus C2 times e to the x plus C3 times e to 2x. But that is exactly what you get when you apply T2 C1 plus C2 times x plus C3 times x squared. So T is onto. Since it's onto between two finite dimensional spaces of the exact same dimension, consequently, hence, T is 1, 2, 1. So therefore, this mapping is onto and one-to-one. It's an isomorphism between the spaces. The spaces are isomorphic. You can then use this argument always. For any two spaces that have the same dimension, this argument will always work. And that's it. That's it for this particular video.